So this is the first in a series of videos that are going to cover the core practicals for Unit 3. This video will cover core practicals 1 and 2, and the subsequent videos will cover core practicals 3 to 8. For the first core practical, it is how to measure the molar volume of a gas. Now this is going all the way back to topic 1, which was our calculations topic. So the experimental objective here is to find the volume of 1 mole of carbon dioxide gas, or its molar volume. Remember, the molar volume of any gas will be the same given a specific temperature or pressure. What we can do is carry out an experiment, collect the gas, and from our results we can plot a graph and we can then determine our molar volume. So how do we do this? Well, we measure out 30 centimetres cubed of 1 mole per decimetre cubed ethanoic acid. We then transfer that into a conical flask. We attach the conical flask either to a gas syringe or a delivery tube to allow collection over water, and we'll look at both of these setups in just a minute. We measure the mass of a weighing bottle with approximately 0.5 grams of calcium carbonate. We then add the calcium carbonate to the conical flask, quickly resealing the bung to make sure that no gas escapes. This is extremely important. We then allow the reaction to be carried out, and when the reaction stops, we record the final total volume of gas. We then reweigh the empty test weighing bottle that we used back in step 3, and we repeat the experiment several more times, increasing the mass of calcium carbonate each time by about 0.05. You would probably need to do this experiment maybe 6 or 7 times to get a nice set of results that we can then use in a graph. So the method that we use is one of 2 ways. We will either use a gas syringe or we will collect the gas over water. So this is our equation here, where you can see that we have a 1-to-1 ratio, and most importantly, this creates a gas. If we use the gas syringe, the gas is formed, travels through the delivery tube here into the gas syringe, and it pushes the plunger back, and wherever it finishes is our end volume. Alternatively, we can collect the gas over water so that it passes through the test tube, through the delivery tube, up into the measuring cylinder. It displaces the water, and again, wherever our final measurement of our water gets to, that is the gas volume that we have used. So some example results where we would take the mass of our calcium carbonate and we would plot it against our volume, of course our mass being our independent variable and our gas being produced as our dependent variable. We should get a lovely straight line, but you may find that you have to use a line of best fit, but that's okay. We can then determine from the graph the volume of carbon dioxide that's produced for any specific mass of calcium carbonate. So let's say, for example, we've used 0.25 grams of calcium carbonate, and let's say that that's here. I draw a straight line up, or as straight as possible, of course with a ruler, to the line, and then across, and I measure that volume, and in this case, let's say that it is 61 centimetres cubed. I can then determine my number of moles by doing my mass divided by my molar mass, and that gives me 0.0025 moles. They are then in a 1-to-1 ratio, and it gives us 0.0025 moles of CO2. I can then take my volume and divide it by my number of moles, if you remember your triangle for molar volume, and I determine that my molar volume is 24.4 decimeters cubed per mole. Therefore, for this particular reaction at room temperature, very important, our molar volume of carbon dioxide is 24.4 decimeters cubed per mole. Now, very important that we remember that molar volume will change depending on the temperature of the gas. However, we do determine the majority of almost all of our molar volumes at standard temperature and pressure, which is 100 kilopascals and 298 Kelvin. Some key points For this experiment, we want to wait until we have no effervescence being observed before we make any weighing, reweighing any of the flask and the marble chips, because we want to make sure that we're minimising any gas loss and we want to make sure the reaction is fully complete. We don't want to use too much calcium carbonate because we don't want to make any more gas than our measuring cylinder or our gas syringe can fit. We want to use a weak acid, such as ethanoic acid. We want to avoid things like hydrochloric because we want to make sure that our reaction is quite slow, because again, that is going to minimise our gas loss between adding the marble chips and reattaching the bung. If we want to avoid having to reattach the bung at all, what we can do is we can put the marble chips onto a string in the bung, seal the test tube, and then tip the test tube so that the acid comes into contact with the marble chip. This reduces any loss of product and it makes our results slightly more accurate. However, with any practical, we can always expect errors. For our syringe, we need to make sure that it's free moving. If not, we do need to use a lubricant so that we can get our gas pushing the syringe to give us our final volume. One major problem with this reaction, if we do the collection over water, is the fact that CO2 is slightly soluble in water. So our exact volume may be slightly off. So you probably find that you're going to want to do this reaction with a gas syringe just to avoid that. As we've covered, we can get some gas escaping when we get our marble chips being added and the sealing of the test tube. We could also have a bung that is not airtight. Of course, these are all going to affect our results. One of the major errors that could come through is in the transfer of the solid. It is extremely important that we weigh the test tube or the bottle, whichever we use, with the marble chips before the addition and after the addition, and we call this weighing by difference. This makes sure that we know exactly how much product that we have used, because when we transfer between different containers, we can get some trace being left over. So by weighing by difference, we know the exact amount of the calcium carbonate that we have added. You will see weighing by difference coming through in a number of different experiments throughout this course. Now, unfortunately, I have not been able to find a past paper question for this particular core practical. That does not mean that they will not come up though. The majority of questions like this will be in the form of a calculation but they can always ask you about the actual practical part. Okay, so moving on to core practical 2, which covers everyone's favourite reaction, which is Hess's law. So we're going to use Hess's law to calculate the molar enthalpy change for two reactions, and then use the Hess's law to determine the enthalpy change for a reaction that we cannot measure. So the reaction that we can't measure is the decomposition of potassium hydrogen carbonate. We can't measure the temperature directly because it requires heat in order for us to start the reaction, and that will have an effect on the measured delta T. But we can carry out two different reactions and of course use Hess's law. Now, as a reminder from our Unit 2 lessons, Hess's law states that the enthalpy change of a reaction is independent of the path taken to get there. So whether you go from A to B or you go from A to C to D to B, the reaction enthalpy is going to be the same. And we're going to use that same principle to help us with a particular reaction with regards to decomposition. So our apparatus that we're going to need, well, we're going to be doing a neutralization reaction. So we're going to need some hydrochloric acid, we're going to have some potassium carbonate, and some potassium hydrogen carbonate. Of course, we're going to be measuring a temperature change, so we need a thermometer, a polystyrene cup used to insulate the reaction, a beaker, some test tubes, a burette, a stirring rod, a mass balance, and of course a spatula. Safety, as always, we want to wear eye protection and suitable chemical resistant gloves, and we want to avoid skin contact with any of our reactants or our products. So the method for this is quite straightforward. We want to take 3 grams of the solid potassium carbonate, put it into a test tube, and then accurately weigh the test tube and its contents. We then want to use a burette to add exactly 30 centimetres cubed of 2 moles per decimetre cubed dilute hydrochloric acid into a polystyrene cup which is supported by a beaker. So the polystyrene cup is there to minimise our heat losses because of course it is an insulator, but the biggest problem is that they are very light. So the smallest hit they can completely tip over. So we put it into a glass beaker that's quite heavy that avoids that potential spillage. We then measure the temperature of the acid, and this is going to be our starting temperature. We gradually add the potassium carbonate, constantly stirring and monitoring the temperature until we get up to a maximum temperature. We then reweigh the empty test tube. So remember, that was what we discussed in Core Practical 1, and it's known as weighing by difference. That tells us the exact amount that we have used of the potassium carbonate. We then repeat the entire experiment again, steps 1 to 6, this time using 3.5 grams of potassium hydrogen carbonate, and we record the temperature that we reach. So what do we then do with our results? Well, we can calculate the energy released using Q is Cn delta T. We can then use that to calculate delta H, which is our number of moles, which is our energy change per mole. So we can work out how many moles of our potassium hydrogen carbonate or potassium carbonate that we use. We can construct a Hess's cycle from these two reactions, which are neutralizations, to give us our target decomposition equation. And the Hess's cycle that we would construct looks something like this. Most importantly, we note that we need 2 moles of the potassium hydrogen carbonate. If I just go back, notice here, I only used 1 mole. So I have to take that into account, that everything in reaction 2 is actually going to be multiplied by 2. So delta H1 in my calculations is going to need to be multiplied by 2. I'm using 1 mole of the potassium carbonate, which if we go back, again, that's the same, so we don't have to make any sort of multiplication there. And we can use Hess's law to determine the delta H of the reaction. Major errors that can come up, and this typically comes up in exam questions, so it's important to know these, is that sometimes our energy can be transferred to our surroundings. We need to take into account that we do get heat loss. We also make 2 very large assumptions, and that is the second and the 4th bullet points. We make the assumption that the specific heat capacity and the density of our HCl is assumed to be the same as water. Now, whilst the bulk of this aqueous solution is water, the HCl can have a small effect on it, but we avoid that in our experiment and we simply use the specific heat capacity as 4.18, and we assume that the density is 1 gram per centimetre cubed, meaning that 1 centimetre cubed of the liquid is equal to 1 gram. We also ignore any energy that is absorbed by the polystyrene cup. So let's have a look at a past paper where we do this exact reaction. I went back to June 2012. There are some other questions on this, but this is a specific to the potassium carbonate reaction that we're looking at. So we've carried out our 2 reactions, and in this case we're looking at delta H1, which is the potassium hydrogen carbonate, and I get these results here. So part 1 is asking me to calculate the heat energy that is absorbed in joules by the reaction of the potassium hydrogen carbonate. So they even give you that Q is equal to 25 times 4.18 times the temperature change, and the temperature change is the difference here, which we can see is 10. We put this into our calculator and we get an answer of 1045 joules, or 1.045 kilojoules. Whether you choose to convert it here or convert it later on is completely up to you. Just make sure that you do always put it into kilojoules per mole. We can also calculate then in part 2 our number of moles. Our number of moles is the mass divided by the MR. Our mass is 3.48 and our MR is given to us as 100. So our number of moles is 0.0348. Part 3 then asks us to calculate the enthalpy change for this particular reaction. So delta H is equal to Q over N, which is 1.045 divided by 0.0348, which gives us an answer of 30.03 kilojoules per mole. Now this would only get you 1 mark because you must always include a sign in your reaction. And if we notice here, our temperature has went down from 22 down to 12, so this is an endothermic reaction. So our answer is plus 30.03 kilojoules per mole. You can get transferred errors if you do make a mistake in part 1 or part 2, but these are fairly straightforward calculations, so hopefully we can avoid any errors like that. Part B then goes on to talk about delta H2, which is our second reaction. And it is saying that for this particular reaction, the enthalpy calculated was minus 34 kilojoules per mole. Just a reminder that delta H1 is plus 30.03 kilojoules per mole, because we are going to need to use that answer. So we need to state one way in which the temperature change is different between these two, where we can see there is a complete difference between this value and this value. The thing that should stand out to you most is the fact that they are two different signs. So there are two different ways that we can answer this question. We can either say delta H1 is endothermic, whilst delta H2 is exothermic, or we can say that delta H1 has a temperature decrease, whilst delta H2 has a temperature increase. Either one would be an acceptable answer. What we do need to make sure that we do is that we have both of them. This is a compare answer, and even though it is only for 1 mark, we have to have both H1 and H2 being referred to in our answer. And part 2 is talking about the assumptions. This is going back to that previous slide where I said that this will come up, and we can give various different answers here. So we can either be talking about the density, we can talk about the specific heat capacity, assumptions that they are the same as water. We can either say that there is the assumption that we have no heat loss, or that the reaction is incomplete. So there are 4 possible answers here. One that will not be accepted is about the thermometer or any of the actual equipment being inaccurate. That is not an assumption that we have made. We make the assumption actually that those are all correct, and they will have no bearing on our calculation. Part C then takes us into our actual Hess's law. Now, what you'll tend to find in a Unit 3 paper is they will give you the Hess's law cycle. They tend not to ask you to do that. That's typically reserved for a Unit 2 paper, because this isn't about can you draw the Hess's cycle, it's can you use it. So we have then been told that delta H1 and delta H2 can be used to determine this reaction here. Okay, now if we go back and we look at our delta H1, we notice again the same thing. We have 1 mole here, whereas in our Hess's cycle we have 2 moles. So we have to make sure that we know that delta H1 is going to be multiplied by 2, and here this is delta H2, and we want to work out what the reaction is. So our Hess's cycle, we follow the arrows. So we are saying that going from here to here is the same as going from our reactants to these products down to these products. Therefore, 2 times delta H1 is equal to delta HR plus delta H2. Now, of course, we don't want it in terms of delta H1, we want it in terms of delta HR, so we just have to rearrange. And we get 2 times delta H1 minus delta H2. And lastly, we want to physically work out what the answer to this is. So just as a reminder, delta H1 was 30.03 with a positive sign, and delta H2 was minus 34 kilojoules per mole. So let's use those values to determine our answer. So we're going to have 2 times delta H1 subtract delta H2. Well, that gives us 2 times 30.03 subtract minus 34. And we should get an answer of positive 94 kilojoules per mole. Again, making sure that we have our sign, because we do get 1 mark for the sign. This is a 2-mark question. If you forget that positive sign, you are throwing away a mark and you would only get 1 for getting 94. Significant figures are not a major issue here. Just make sure you do not have 1 significant figure. Always have a minimum of 2 or 3. Okay, that is all of our content for Core Practicals 1 and 2. We can check our answers to our past papers here on the mark scheme. You can see we get an answer of plus 94 kilojoules per mole. So the mark schemes are there should you wish to have a look at them. That's everything for this video, and hopefully I'll see you again when we cover Core Practicals 3 and 4.